Hi all, this is Mr. Yeager for Honors Chemistry, and we are beginning our unit on chemical bonding, which is a large unit looking at many different types of bonds, the character, the shapes, basically many different properties that help govern why they react like they do, okay? So we're starting off this first lesson on just what is chemical bonding and looking at ionic bonds and everything about ionic bonds, all right? So, as I just said, we're going to really focus on ionic bond character, which basically is saying, describe an ionic bond to me and everything that goes with it, and then ionic bond naming and formula writing. So, taking a quick step back first, okay? Forming chemical bonds, this is it. The chemical bond itself is a force that's holding the two atoms together. I think most of you guys already kind of assumed that. It's what is holding two different atoms, they could be two of the same types of atoms, together, all right? And again, that forms a compound. They are formed for two reasons. Either there's the attraction between a positive nucleus and a negative electron of another, and negative electrons of another atom, okay? Or there's the attraction between positive and negative ions. All right, so either we become, the atoms themselves actually become charged and become ions, or where there's this general attraction to another atom's electrons that pulls that one closer, okay? So, we got to talk about the valence electrons again. As mentioned earlier, these are the ones involved with chemical bonds because they're on the outside. We want the atoms to be able to create that octet rule. They want to try to get a full outer energy level, which usually means 8 electrons. The bonds, when the atoms are bonded together, they are generally lower energy than the individual atoms. So in other words, the compound that is formed is a more stable situation in many cases than if the atoms are left by themselves. So again, this is why we don't see alkali metals completely alone. We don't usually find elemental alkali metals, but we will then find alkali metallic ions in multiple compounds because that's where they form. Okay? So, we're only looking at ionic bonds right now. When we form ionic bonds, it's because you have the charged ions, they attract to each other, a positive and a negative. It sort of goes back to that Coulombic attraction that we talked about when we did periodicity. The electrons are completely transferred from one element to another element in an ionic bond. All right, so the anion completely takes control of an electron that might have come from a cation, and then those charged particles attract. They're always formed between a metal and a nonmetal. They're held together by what we call electrostatic force between charged particles. Okay? And then we also call ionic compounds salts. All right? Which, can be misleading because you think of salt as table salt, something that you eat, or sea salt, again, something that you eat. Well, it turns out it's because those particular salts are actually ionic compounds. All right? Another name for ionic compounds is formula units. That basically, we'll talk about that a little bit later, but essentially kind of giving you an idea of it. When ionic ions come together, they form a crystal structure, and it's a repeating pattern where the formula we are getting is actually just a ratio of how many of the cations we have in relation to the anions. There, I guess I just explained it anyway. Okay? The last thing is the overall charge of an ionic compound has to come out to 0. Again, that's just going to help us figure out how to do the compounds themselves. So, properties of ionic compounds. They form crystals. So this is the idea of formula units. Okay? These crystals and so forth that I am showing over there, the idea is when we have an ionic compound, it's not just one Na cation and one Cl anion. It is millions of these that create a nice crystal arrangement, basically, again, a nice geometric arrangement, essentially, and that's what we call a crystal then. They create what's called a crystal lattice, okay? I'll actually draw it out real fast for you so you can see that. So, the idea is something like this, where we have an Na plus, Cl minus, Na plus, Cl minus. So we kind of get this arrangement, and that's obviously a 2D arrangement, but then expand this into 3Ds, and that's how we can create these crystal lattices. All right? Ionic compounds, they have high melting and boiling points, so they will be generally solids initially. Ooh, there we go. Okay. They are hard, rigid, and brittle solids. Okay. Again, when we say brittle, it just means when we try to break them, they kind of will shatter quite a bit. Okay? They're non-conductors when solid because they have no charge when they are together. They have zero charge. But they are conductors when dissolved, which is what I'm trying to show with this little picture right here, the idea of what's called an electrolyte. Okay? An electrolyte is where those individual atoms, the charged ions, are freely moving when they dissolve. They are able to split up the crystal lattice some, and then the electrons are able to travel through them very easily. So we call that electrolytes. Okay? So that is exactly the same. That's where, again, like Gatorade likes to say, we fill you with electrolytes, which just sounds so much because of energy. Well, we do need that type of solution. It's basically salts that helps move the energy in and out of their cells to be able to do what you need to do. So let's get to the naming and formula writing. Okay? So so basically just throwing an example right out at you first off. So we have CaF2. Now one of the things is, first off, why is this an ionic compound? This is an ionic compound because Ca is a metal and F is a nonmetal. Okay? And we always will write it metal, nonmetal. Okay? So we got that. This is a binary ionic compound that I'm showing here. We do have other types. Okay? The metal will always just keep its name. The nonmetal will add the suffix "ide" to it. Okay? And that's it. So to name this compound, we would just say calcium fluoride. Done. We're not paying attention to the number at all. We'll figure that out in a minute, where that number comes from. If I'm naming just a binary ionic compound, where I have a metal and a nonmetal, a cation and an anion, I just give the metal its name, calcium, and then I change fluorine to fluoride. All right. So some other ones. BaO, that would be barium oxide. Li3, that would be lithium nitride. Okay, lithium nitride. And then Al2S3, that would be aluminum sulfide. Okay, that's it. I mean, so naming, at least initially right here, seems kind of straightforward. This seems not so bad. Okay, but we do have some exceptions and things like that. All right. We're going to jump to formula writing for all compounds. This doesn't matter what type of, whether it's a binary ionic or any of the other ones I'm about to show you. Okay? The overall charge of that compound must be 0. So, let's go with an example. I have lithium phosphide. Okay? I know this is an ionic compound because it's a metal and a nonmetal. Again, I'm going to keep saying that because eventually, when we actually take a test or something, it's going to be where all of these compounds are all together, and we have to identify, is it ionic, is it covalent, and what do I need to do? So this is what I would recommend doing. Okay, identify the charge of each element, determine if you need more than one ion to balance the charge, and then write the chemical symbol and a subscript after the symbol to show the number of ions necessary. So identify the charge, determine if you need to balance it. In other words, if they're not equal charges, that means I need more of one versus the other. And then write the chemical symbol and a subscript of how many you want there after the symbol shows the number of ions. The last step where you got to be careful, because I'm going to show you another quick rule too, is you have to have the lowest ratio of subscripts. So I'll go ahead and point it out now. I mean, we'll go ahead and just do this one. So what I do here is I go, this is +1. And this is -3. How am I figuring that out? I look at the periodic table. We should know how to figure out the charges now. But you can see that they are not equal in charge. The overall charge has to be 0. I'm going to put a little plus sign. In other words, when I add these up, I need to have it come out to 0. Right now, it's not true. So I need to change how many I want of each one. I cannot reduce the -3 to -1. That's not allowed. I can't change that lithium is +1. But what I can do is I can say, well, I want 3 lithiums, because 3 times +1 is +3, plus -3, guess what, equals 0. So I'm going to need 3 lithiums, so this would be Li3P. Okay? And that's my official answer for this one, lithium phosphide. All right? And I think it's going to happen on the next pages, even if I don't care if doing it again. All right? But what I mean by confirm the lowest ratio, this is the lowest ratio. I can't get lower than 3 to 1. In other words, I can't divide both of those numbers by the same number and not get a decimal. I'd have to have it come out to a whole number. Now, if I have something where this is just completely made up, Li3P3, and I said that's quote unquote the correct answer, that is not the correct answer, there's no reason that I would need to keep 3 and 3, and I would reduce this to LiP. Okay, that's the idea of reducing the ratio. Okay, but again, that's completely wrong formula there. All right, so let's move on with that. So I think I actually go through this one step by step. So lithium phosphide, +1, -3. This helps us to see it again. All right, you need 3 lithium atoms, so I can multiply that by 3, and there I go, Li3N. Okay, so if I have 3 Li's and 1, why do I have N there? That's a nice move there. Yay, that really helps. That makes a lot of sense, right? This should be Li3P. Whoops. Okay, nice job. All right, Li3N would actually be correct, but that would be lithium nitride. Okay, all right, so my bad there. So this should be Li3P. There is also what's called the crisscross method. Let's see if this comes out to Li3N again. Okay, a lot of students like this, but this is where the ratio needs to be paid attention to. If you identify the charge, you can do what we call a crisscross method, where you basically just bring the charge down to the opposite atom, and that will tell you, yeah, Li3N. Where the heck did I get that from? All right, that will give you the correct formula. But this is one where we got to be careful, and I'll show it on future examples. Like, this is correct in the end because that's the lowest ratio. If I crisscross charges and I don't have the lowest ratio, your atom, your compound is incorrect. Okay, I apologize about the N versus the P. Okay, so now the other thing you notice here, we don't ever write the subscript 1. If I write down the element there, I know I have 1 there. I need to know whether there's 2, 3, 4, 5, 6, 7, 8, etc. Okay, so here's some more practice. Rubidium chloride. So here we go. Rubidium is +1, chloride is -1. Do you like the crisscross method? Sure. Well, it's 1 to 1. So this would just be RbCl. Okay? RbCl. Yay, that one's right. Okay? Aluminum nitride. This would be +3. This would be -3. Right now, these are kind of simple because the charges are equal, so I don't need to change any of them at all. But I can crisscross, and I would see some people say Al3N3. That is incorrect. I need to reduce the ratio from 3 to 3 down to 1 to 1. It should just be ALN. Okay, ALN. I think we got one more. Strontium iodide. This would be +2, -1. I would need 2 iodides, or I crisscross, and I can see not 2 to 1. And this would be SRI2. Questions? Hopefully not. Well, you can't answer them right now, can you? Or have them. All right, what about binary compound with transition metals? Okay, so when we have transition metals like this one, this is Mn2O7. All right, the formula writing for it is the same. I mean, we might have an example here, we might not. I'm going to naming this. All right, the transition metal will keep its name. The issue that we run into is now you need to write a Roman numeral that represents the charge of a transition metal, because transition metals have multiple charges. All right, the nonmetal will keep its name I, so nothing too special there. But the issue we run into is, how do I figure out the charge of the transition metal? How do I figure out the charge? Okay, so for MnO2, it's manganese. We know that. Okay. We know the charge of oxygen is -2. That's the thing, is we will always know the charge of the other element. And I usually like to draw it out and put a line in between them. Okay? Because I know all the oxygens are -2 and there's 7 of them, there's a total of -14 charge coming from the oxygen. Which means, I'm going to finish this up by writing it, I need a +14 charge from manganese, but I have 2 of them. So I need to divide this by 2, and guess what? Each of the manganese has a 7 charge, a +7 charge. So that's what we got with it. So the 2 MNs must add up to +14. So I divide, and therefore my formula is manganese 7 oxide. VII is the Roman numeral 7. Okay? And we would just say the word 7. Now some people tell me that they like to do a reverse crisscross method. But you got to be really, really, really careful with this, because this one does not work nearly as effectively for a lot of students, because when we get to certain problems, you might go back and forth like this and it doesn't come out to the correct charge because we've reduced the ratio. So you got to be, the reduction of the ratio is occurring last. We don't know for sure what we need to increase it by before uncrisscrossing them. All right, so I don't like that method too much. All right, Roman numerals you need to know: 1, 2, 3, 4, 5, 6, 7. Okay, if you need more time to take a look at them, pause the video. Okay, so let's try a couple here. Fe2O3. Okay, Fe2O3. I know O is -2. There's 3 of them, so this is -6. So this has to be +6. There's 2 of iron, so 2. So it's going to be +3. So this is iron 3 oxide. Okay? And again, I have to do that because this is a transition metal. I haven't done this before because all the other examples, if they're a metal from column 1, column 2, or column 13, the boron group, they always have the same charge, so we don't worry about that. Okay? Au2Se, all right? Au2Se, this would be, Se is -2. There's only 1 there, so this other side has to be +2. There's 2 of them here. The gold has +1. Gold 1 selenide. Okay. All right. And then SN3N4. Now I did this one because if you find SN's not in the transition metals. We have to pay attention to PB and SN. They are in the C group, which is the one I called the switch, so we don't know exactly what the charge is. Lead and tin are like transition metals. They could be +2 or +4 at any time. So for this one, we have to go, okay, nitrogen is -3 times 4 is -12. So this is +12 divided by 3 is +4. So this would be tin 4 nitride. Okay. There you go, there you go. All right, here's some more. You can kind of go through it yourself. Oh, yeah, sorry. This is going from name back to formula. This should be a lot easier because now I'm giving you the charge. So the idea here would be lead 2. So lead is +2, sulfur is -2. I could crisscross here, but they're equal charges, so that's why you saw PBS. Okay, I'm going to move through these a little faster. The second one, niobium 5 fluoride. Niobium's 5, fluoride's 1, crisscross, it'd be NbF5. Platinum 3 oxide, crisscross, +3, -2, PT2O3. So again, name the formula is kind of more simple there because the biggest thing just to remember is that the Roman numeral goes with the metal. Please don't put it with the anion, okay, not with the nonmetal. Nonmetals have very specific charges. I think the last thing we got here is polyatomic ions, and this is something that you're just going to have to memorize, all right? One of the things that I will make you go through and know these different polyatomic ions, all right? So polyatomic ions are ions that are made up of more than one type of atom. You can see the different examples here, and they see the charge. Again, you will have to know this for the test. I'm going to give you like a sheet of them so that you can use them while practicing, but you're going to have to learn them, okay? With ionic compounds, basically, we recognize that we have a polyatomic ion because we have 3 elements now. Okay, there's 3 elements here. All right, I think they're sometimes called like not tertiary, but I don't know. You got 3 elements, so it's not going to be just a binary compound. All right, the metal keeps its name. If it's a transition metal, include a Roman numeral. The polyatomic ion keeps its name. So that's where if you learn all the polyatomic ions, which I know will take some time, it just keeps its name. Okay. So that one right there was calcium carbonate. Okay. Other examples, this would be magnesium, and ClO3 is called chlorate. AgNO3, Ag is a transition metal, so I would need to put the Roman numeral with it. So that would be silver, and NO3, actually, I'll go and do this one a little bit more. This NO3 on this side is -1, so this is +1. So this would be silver 1, and NO3 is called nitrate. And then K2C2O4, that's called potassium oxalate. Okay. If I go from name back to formula, I need to again recognize the charge, and I write out the polyatomic ion. So again, figuring these guys out, Molybdenum is +2. Permanganate is a polyatomic that's -1. I can crisscross the charges. I write MO, and then permanganate is MnO4 2, because I'd crisscross the charge. The 2 would go to the permanganate. Now you can see what I do here. If I have more than one polyatomic, I have to put it in parentheses, because I can't sit there and go MnO4, MnO4 2, because now it looks like you have 42 oxygens. So we got to put the polyatomic protected in the parentheses. Okay, I think MO, yeah, MO. Okay, MO, MnO4. Shoot, I made a mistake on that one. Sorry, guys. I'm catching some of my mistakes on my new presentations here. Okay, so that should be 2. All right, calcium percolate. Calcium percolate, that one would be CaClO4 2. Okay, I'm really sorry here. So again, the new presentation, I didn't catch some of these mistakes. So again, these should be 2s. All right, so if you check out my presentation later, if you go on It's Learning to check it, you'll see it is corrected. Ammonium hydroxide, NH4OH. You actually have 2 polyatomics there. Ammonium's the only positive polyatomic, and it's +1, -1, crisscross. Okay, so again, sorry for those last mistakes, but we are done, and I'm going to go back and fix them. All right, thank you very much. Have a good one.